Hello, my name is Nislav Aranovsky and I would like to present you our research on state estimation for a locally unobservable system. The outline of my talk is given on the slide. I will start with a motivating example where I will also show you why some standard solutions do not apply. Then I will present you the problem statement and two solutions that we propose, one nonlinear observer and one switched observer. Then I will present you some examples and the concluding remarks. Our motivation comes from a robotic application where we use a reaction wheel inside a robot to stabilize it in vertical position. It can be shown that if our angular measurements are biased, then our system can be written in the form given on the slide, where z is an external signal and our goal is to estimate the state x. The problem of state estimation is that the observability matrix, which is also given in the slide, becomes singular for certain values of z. So we need to estimate a system that can be unobservable for certain values of input parameter. What are possible solutions for such a problem? Well, one classic solution is to design an LTV observer, which is a very well known and is given in the slide. And it's known that if our system is uniformly observable, then we have exponential convergence. So what's the problem with this observer and why we don't want to apply it in our design? Well, to compute the matrix H, we need to solve online 6 differential equations with quadratic terms, which can be quite demanding for numerical accuracy, and it's not really a good idea for embedded solutions. So what we would like to have, we want to find an observer that is less demanding for numerical accuracy and where as much as possible can be pre-computed in advance in offline way. The simplest possible solution is just to consider a constant gain observer. But since our system is not observable for some values of z, it's obvious that such an observer does not exist. So we have to consider a parameter varying gain L of z. And if we choose a standard observer structure and consider a quadratic polynomial function with a matrix P, then we have several options for P. So the simplest one would be to have P as a constant matrix. But it can be proven and it can be shown that if we choose P of z as a constant matrix, let's say P0, then such an observer does not exist. So we have to consider matrix P which depends on z. And if we consider P of z which is continuous in z, then when we compute time derivative of V, we have to impose several assumptions on z dot. And it can be restricted. We don't want to do it. So what do we propose? We propose two solutions. The first one is a nonlinear observer where we create a new output which has several nice properties and allow us to design an observer. And the second solution is a switched observer where we consider P of z as a piecewise function of z, which means that we don't need to impose assumptions on z dot, but instead of this we need some assumptions on average dwell time, and we also have to study possible jumps in P of z. Let us now consider a more general problem statement. Again, we consider a linear system, but now we have two input parameters, Q1 and Q2, and our system is not observable if any of these two input signals is 0. So this system is equivalent to the previously considered one if we say that Q1 is identically 1 and Q2 is a cosine of z. And we still have the same goal. Our goal is to estimate the state x based on the measurements y, even if the system is not observable for some values of input parameters. We start with a nonlinear observer. The main idea here is that if we are not happy about the given output y, then probably we can design a new output y dagger that has some nice properties and that can be used for observer design. More precisely, we would like to define y dagger in such a way that the new output matrix W is persistently excited. If we can construct such a matrix, then we can use standard observer design tools from the adaptive control. Okay, so how can we do it? First, we define two new variables, phi1 and phi2. The phi1 is a linear filter for q1, but phi2 it's already a nonlinear system because we have this product of phi2 and q2. The output y dagger is defined in this way, where our xi is also a linear filter for some non-linear combination of the available signals. And given these definitions, and using the swapping lemma, we can show that this relation holds where our new output matrix W is given by this equation. So how can we use this design for observer, for the state estimation? Well, first we need to assume that our W is persistently excited. So we assume that our trajectory Q of t, our input signals, are such that W is persistently excited. And then we can design the standard nonlinear observer. So we reproduce the dynamics of the system and add some correction. And if we have the persistency of excitation, then our observer is exponentially stable for all sufficiently large gamma. The proof is rather straightforward and is based on the aerodynamics analysis. So we have new convergence conditions. Our intuition says that if the original system is not uniformly observable, then W is not persistently excited. However, it's not clear if the uniform observability of the system is sufficient for W to be persistently excited. So probably there exist trajectories Q of t such that the original system is uniformly observable, but W is not persistently excited. In what follows, we will consider a switched observer that has different convergence properties. Let us now proceed to the switched observer. So what is the main idea behind the switched observer? The system itself is not switched, but our input signals Q of t, they live in a square, because Q1 and Q2 are both from -1 to 1. So we can divide this big square in 4 smaller squares, and when our trajectory is inside each of these squares, Q1, Q2, Q3, Q4, the system is observable. So the system loses its observability only when the trajectory travels from one calorie square to another. And here we have a very natural idea. Even if the system is not switched itself, we can write it as a switch system where we switch each time when our trajectory Q of t travels from one square to another. So we basically design 4 observers, one observer for each square, and we switch between these observers. And then we need to have each observer stable, and we also study what are the jumps in the Lyapunov function when we switch between different observers. The first step to write the switched observer is to write the original system in the switched form. To this end, we define the matrix AS that takes one of 4 values A1, A2, A3, and A4. It depends on the trajectory Q of t in which square it is at the moment. And each of these A1, A2, A3, A4 is like given in the slide. We also define the function Fs, which is a function of Q and X, and it basically gives us the distance between the real value Q and its value in the corresponding corner. So it's a difference between the value of Q on the trajectory and the value at the closest corner. And with the given definitions, we can rewrite the original system in the switched form. So this system is exactly the same system as we considered in the problem statement, but now it's written using this switched matrix. So we can also construct the switched observer. As usually, we reproduce the behavior of the system and we add the corrective term. So now the problem of observer design is to find such gains L1, L2, L3, and L4, one gain for each of the squares, such that the overall system is stable. So let us start designing the gain L1. So the gain L1 is such a gain that it should stabilize our observer when our trajectory is inside the first square. And our system loses observability when trajectory Q of t crosses the axis. So to have our problem well posed, we need to introduce some delta gamma, which is basically the distance between the axis, where our observability matrix becomes singular, and the area in which our observer will walk. So we introduce this delta gamma to make the separation, and then we need to design the gain L1 such that our observer is converging for all possible trajectories Q of t inside the green square. So we don't even need to assume that Q of t is continuous. It can be jumping trajectory or whatever. The only thing that we need is that Q of t remains in the green square. And designing a gain vector for observer that is stable for all trajectories, it's basically an LMI problem. So the gain L1 is stabilizing for Q1 if this LMI is feasible. And this is a standard LMI for observer designs. So we have the quadratic Lyapunov function, and basically this lemma is feasible for all suitable choices of delta gamma. And as a result, we have the gain L1, which is stabilizing for L1, and then we need to design L2, L3, and L4 for all other squares. And the good news is that as soon as we have L1, we don't need to solve any new LMI for L2, L3, and L4 because all these gains can be computed directly based on the L1. So we need to solve only one LMI for all four squares. As a result, we also have P2, P3, and P4 that can be different from P1. So if we have quadratic Lyapunov function, this one for the first square, we will have similar quadratic Lyapunov functions for all other squares, but this function, they share the same estimation error vector, but they have different matrices. And as a result, when our trajectory travels from one square to another, we will have changes of the Lyapunov function, so we will have jumps. And the question is, if we design an observer using these gains, what are the convergence conditions? So let us consider some trajectory which travels between different squares. We have this gray zone, and the first important consideration for us is that in this gray zone, our Lyapunov function can be increasing, because we choose our gains such that they are stabilizing inside the colored squares, but between them, it's probable that V dot is positive. And the second important consideration is that, as we have just discussed, when our trajectory travels from one square to another, we change matrix P in our Lyapunov function, so we have jumps. So the basic idea for convergence of the observer is that the system does not spend too much time in the gray zone, and that it does not cross this border too often. So these conditions can be formulated as an inequality, which is given in the paper. And the basic idea behind this inequality is that we don't cross this border too often, which is given by the constant NQ, and that we don't spend too much time inside the gray zone, which is defined by this integral. So if our trajectory satisfies this assumption, then our observer provides exponential convergence. The convergence condition for the switched observer is different from the persistent self-excitation that we had for the nonlinear observer. So, as a result, we have two different observers with two different convergence conditions. Next, I would like to present you some examples. So, we start with an illustrative example where we have two time-varying parameters Q1 and Q2 that are varying as given on the slide. So, the whole trajectory Q of t given in this figure travels between all four squares. And the states of the system are shown in this figure. So, our goal is to estimate the states. We apply both the nonlinear observer and the switched observer, and as it can be seen from the figures, both observers are working pretty well, so they both provide convergence of the estimation errors to zero. What is also interesting to see is the Lyapunov function for the switched observer, because here we can definitely see the jumps in the Lyapunov function. These jumps are exactly the moments when we switch between P1 and P2 or P2 and P3 and so on. Besides the illustrative simulations, we also consider one experimental setup. So we consider the reaction wheel pendulum, which is similar to the robotic equipment that we had as a motivation for this talk. And as I have told in the very beginning, if in such a system we have a constant bias in the measurements, which is given by d here, then for this state vector, where theta is the position, theta dot is velocity, and d is the bias, the system can be written in this form, which is exactly the same form as we had in the motivating example. So the system is not observable when cosine of y is 0, and our goal is to apply a switched observer that we have designed to estimate the state vector. So the experimental results are given in the slides. We consider the standard swing up and stabilize problem, and we use our switched observer to estimate the position, velocity, and the bias. And the black lines show us the levels of the signal y at which the system is not observable. So our switched observer switches when the trajectory crosses these black lines. So the observer is working pretty well, and it provides us with good estimates of the velocity, and we also have the estimate of the bias. Finally, I arrived to the concluding remarks. So what we have done, we have considered the state estimation problem for a system that is unobservable for some values of the input parameters. To solve this problem, we have proposed two solutions. The first one, it's a nonlinear observer, which is based on a new output, and its convergence conditions is related to the persistence of excitation. The second solution is a switched observer, where the convergence condition is the average dwell time condition. We have shown that these observers are working pretty well in simulations, and we have also experimental setup for the switched observer. Finally, I would like to acknowledge the financial support for this research from our countries, and thank you for your attention.